Hello everybody. Now I would like to show our research, which is chloride diffusion of alkali-activated flash slag concrete. Corrosion of reinforcement steel is closely linked with our life, and we can see it everywhere, especially the bridges and general structures under marine conditions. It led to 80% of the deterioration of reinforced concrete structures. After 1950, chloride attacks has been considered as the main cause compared with carbonation. Almost 3.4% of global GDP has been used to prevent and repair the damage caused by chloride-induced corrosion every year. Let's see the process of chloride-induced corrosion of reinforced concrete structures. In Australia standard, the total service life of general structures should be around 50 years. For bridges, it should be more than 100 years. The total service life includes initiation period and propagation period. In this research, we focus the first period. It means we need to find a kind of new materials instead of ordinary Portland cement to prevent chloride diffusion. Alkali-activated materials, as known as geopolymer, are considered a good choice. Based on different packages such as flash, slag, and metcoally, we can get different types of alkali-activated materials. For high calcium system with slag, the main product is cash. It shows high mechanical properties at room temperature. However, repeat setting, poor workability, and shrinkage limits its application. For low calcium system with flash and metcoally, the main product is NASH. It has high workability and mechanical properties, but it requires high temperature cooling. To overcome the shortcomings of cash and NASH, the flash and slag binary system is designed in this study. These are the motivations of this research. Firstly, we get the mixture with good properties, including workability and compressive strength. After that, we evaluate the chloride diffusion by natural diffusion test and get the chloride diffusion coefficient. Finally, we discuss the effect of different factors, including flash-slag ratio, water-to-binder ratio, alkali content, and sand aggregate ratio. To find the best mixture, alkali-activated flash-slag concretes with different flash-slag ratio, water-binder ratio, alkali content, and sand aggregate ratio are designed, which are shown in this table. Because SL50, W45, and S40 are the same mixture, there are 13 mixtures in our study. A single horizontal shaft concrete mixture was used to prepare alkali-activated flash slag concretes. Firstly, pick the materials, including flash and slag, sand and aggregate, were dry mixed for 2 minutes. After that, the alkali activator was added and mixed for another 2 minutes. Fresh concrete was then cast into cube molds. After 24 hours cooling at room temperature, concrete was demolded and put in cooling chamber before tests. This figure shows the slump of fresh alkali-activated flash slag concretes. It can be seen that all mixture achieved a slump more than 50 millimeters, and most of them were more than 100 millimeters, which means that these alkali-activated flash slag concretes were regarded as flow or high flow concretes. These figures show the compressive strength of alkali-activated flash slag concretes at 7, 28, 90, and 180 days. In general, alkali-activated flash slag concretes had the relatively high compressive strength. When the slag content was more than 50%, water-to-boundary ratio was less than 50%, alkali content was more than 5%, alkali-activated flash slag concretes were higher than 50 megapascals at 28 days. Natural diffusion test was performed according to ASTM 31543. After queuing for 28 days, surface of concrete was sealed with wax, and only the bottom surface was exposed to the testing solution. After that, those concrete were immersed in 3.5% sodium chloride solution for another 90 and 180 days to simulate the marine environment. At the end of each testing age, concretes were taken out from solution and ground into powder layer by layer. Therefore, the fuel chloride content of powder could be measured according to GTG 27098. Those figures show the chloride penetration of concrete as a function of distance to exposure surface after 90 and 180 days. It can be seen that chloride content at exposure surface sharply decreased along the depth. With the increasing depth, the downward trend slowed down until it reached a stable value at around 12 millimeters. Compared with alkali content and sand aggregate ratio, fly ash slag ratio, and water to boundary ratio present a more important effect. Based on Fick-Second's law, chloride diffusion coefficients as well as surface chloride contents of each mixture can be determined by MATLAB. Those are the chloride diffusion coefficients as known as D of each mixture at 90 and 180 days. The water-to-boundary ratio showed the most important effect, as shown in figure. The D increased from 1.1 to 3.2 as the water-to-boundary ratio increased from 0.4 to 0.5. It may be due to the extra water in the alkali activator acts as capillary pores in the concrete, particularly around the ITC. At 180 days, the D of W50 reduced to 1.3, which means a significant pore reinforcement between 90 to 180 days. For concrete with higher slag content, in which more cash gels were formed, the D decreased from 1.8 to 0.4. It may be due to the faster reaction of slag. As a result, pores were filled and the chloride resistance of concrete was improved. However, the decrease of D was more pronounced in SL30 and SL50 at 180 days, which means the continued reaction was dominated by flash. The D gradually decreased with the increase of alkali content. This may be due to the high alkali content can promote a more rapid dissolution of raw materials, and thus the better pore structure of concrete. Compared with other factors, the sand-aggregate ratio had no significant effect. There are the total porosity and process distribution at 180 days. Generally, mixtures with high slag content, low water-to-binder ratio, and high alkali content had low total porosity and small pore size, which means the better pore structure and hence the better chloride resistance. This result is consistent with the change of the D. To sum up, firstly, alkali-activated fly ash slag concretes prepared in this study were generally regarded as flow or high-flow concrete, and they had the compressive strength more than 50 megapascals at 28 days. After that, compared with alkali content and sand aggregate ratio, fly ash slag ratio and water-to-binder ratio had the more effect on chloride diffusion of alkali-activated fly ash slag concrete. Finally, mixture with higher slag content, lower water-to-binder ratio, and higher alkali content had the lower D, which may be due to the better pore structure. Okay, that's all. Thank you for your listening. Any questions?